Dr. Avaru, you can start your.
Yes, yes. I am starting.
Yeah, yeah,
I
okay.
am sharing my
Yeah,
PPT.
please. Your screen is visible.
Good
Yes, yes,
afternoon,
got
all
it.
of you. I am A.V. Narasimha Rao. My presentation is micro machining characteristics of silicon in NH2H added KOH solution. The main mode of this study is improving the etching characteristics of silicon for MEMS applications, for industrial fabrication of MEMS structures by increasing the etch rate of silicon. Microelectromechanical system. Microelectromechanical system is the integration of mechanical elements, sensors, actuators, and electronics on common silicon substrate throughout microfabrication technology. MEMS have two components, electrical components and micro components, mechanical components. MEMS-based devices can range in size from few micrometer to millimeter, have ability to sense actuate on micro scale. Why MEMS? It decreases size, weight, cost, minimize the material consumption, low fabrication cost, low power consumption, high sensitivity and response speed. Array of the devices is possible. Applications of MEMS: automatic, electronics, medical, communication, defense. These are the some of the applications of MEMS applications. Micro machining. Micro machining is micro machining classified into two: bulk micro machining, surface micro machining. In bulk micro machining, produce structures in substrate. In surface micro machining, production of structures on silicon substrate. This is the schematic view. Bulk micro machining further classified: wet bulk micro machining, dry bulk micro machining. In bulk micro machining, etchant is liquid. Advantages of wet bulk micro machining is quick, uniform, very selective and cheap. Simple equipments, batch process, orientation dependent. Etching characteristics can be altered by some additives, so etc. Disadvantages: conformal etching with vertical sidewall is not possible. In dry etching, etchant is plasma. So in dry bulk micro machining, advantages is low undercutting, directional etching, high resolution. Disadvantages: high cost, hard to implement, low throughput, poor selectivity. So wet bulk micro machining further classified into isotropic etching and isotropic etching. In isotropic etching, each rate is same in all the direction. In anisotropic etching, each rate is different in different orientation. So most commonly using isotropic etchant is HNA. Most commonly using anisotropic etchant is KOH and TMH. So, what is the applications of bulk micro machining applications? Fabrication of 45 degrees micro mirrors, AFM tips, MEMS-based blood pressure sensors, micro valves and micro pumps, silicon micro needles, cantilevers for sensors. This is the unit cell of crystalline silicon. So, when anisotropic etching using, so different orientation have different etch rate. So why? Because of this surface orientation of surface have different shape. So like this way. This is the schematic view before and after wet anisotropic etching. So different shapes of structures we are open after etching on silicon wafer. Cavities like this, the shape of cavities is forming on 100. This is 110 surface, means that silicon wafer orientation is 110. This is triple one wafer. So this anisotropic etchants, most commonly using anisotropic etchant is KOH. Why it is using high anisotropic etching, high etch rate, non-toxic and easy to use. Commonly using a mask materials are Si3, N4, SiO2. It has high selectivity with Si3 and H4. So now I am going to present etch rate of this silicon, crystalline silicon. Etch rate is an important parameter to estimate the etching time for fabrication of MEMS structures such as cavities. This is top and cross-section view before and after wet anisotropic etching. So this is our work. Uh, this graph shows etch rate of 100 orientation in pure and NH2OH added KOH solution. Pure and NH2OH added KOH solution. So we extra added NH2OH. So what is the change of this etchant? Anisotropic etchant, etch rate, how it is changed? We are showing this graph. This is pure solution etch rate. After addition of different concentration of NH2OH, etch rate is increasing. At 15%, we obtained maximum etch rate. This is schematic view. Downside we are showing schematic view. So with this modified solution, this is pure solution H rate on cross section view of that wafer. This is modified solution. So modified solution increasing H rate, it will quickly release the structure for required depth. This high speed etching is very useful for enhance the industrial production and quality of MEMS and NEMS structures. Similarly, another orientation 110. Similarly, the teach rate is increasing with NH2OH concentration. Similarly, on triple one also at 15%, NH2OH added concentration gives high H rate, highest H rate. Similarly, we are also studied H rate of silicon dioxide, which are using as mask and structural layer on fabrication of this type of structures, microstructures on MEMS applications. This is pure solution after addition of NH2OH, little bit increasing. So mostly we are expecting low H rate. So but here also that is not considerably increased. So that is one of the advantages of this modified solution. So this graph shows selectivity between silicon and silicon dioxide. So selectivity is increasing with increasing NH2OH concentration at 15%, we get double selectivity compared to pure solution. So selectivity is one of the very important. So to product like this way, this is cross section view of silicon. This is the production silicon dioxide to protect unwanted places. This place is open places, silicon open place. So when dip this wafer inside the solution, only this part only etching. So this product place producting the silicon dioxide. This is product this remaining area. So we want less etch rate of this mask material. So these are also showing better selectivity, means it have we using better mask. See, similarly, this is schematic view. For same depth, this modified solution more this silicon dioxide producing more. So oxide layer can be used as mask layer and structural layer in modified solution compared to pure solution. So this is a graphs of in different temperatures in pure and NH2OH added solution. So in various concentration also we observed high H rate compared to pure solution. Similarly, we are studied silicon dioxide also H rate, selectivity also. At low temperature, we observed high selectivity compared to high concentration. So this modified solution, we added some triton like because some applications we don't need to undercutting. Generally, when using this solution, undercutting takes at convex corner. So for producting, we are added some triton. Only that pure how it is working. Similarly, this modified solution also working. We are successfully fabricated mesa and cavity structures in modified solution similarly as pure solution before pure solution how it is with high speed, little bit high speed. This is different concentrations of some images. Another IPA also we added this modified solution. We observe similarly as pure solution. We fabricated mesa and cavity structures this modified solution similarly as pure solution this with high speed. This is different concentration. Uh, so we are studied this aging effect also this solution. This with aging each rate is decreasing this solution means after preparation of solution we store that each rate is decreasing after using this solution. This is days, this graphs. So this surface morphology is also important. Not only H rate for fabrication microstructures, for some another applications, study of surface morphology is also important. Surface morphology is an important factor in MEMS, especially for optical applications and designing high efficiency solar applications. Surface morphology is primarily affected by etching time, etchant type, its concentration, itching temperature, additives, and external agitations, etc. This is the sum of the images, some images of surface morphology on 100, 110, and 111. 100, 110, and 111. This graph shows surface morphology in pure and various concentration of NH2H added kerogen. So nearly similar surface morphologies, surface roughness is not considerably changed on 100 surface. These are corresponding semi images of that surface. We are also studied on 110 surface. This is the semi images corresponding surface roughness. Similarly, on 11 surface also. This is. So from these three, we are observed that surface morphology is not considerably changing by addition of this NH2H in pure KOH solution. So undercutting at convex corners in pure and modified KOH solution. So this when anisotropic etching, when dipping this solution, so mask layer at mask layer convex corner place undercutting takes undercutting this convex corner places. This is mask where we want product. This place we want to etch. So this convex place undercutting takes. Then etching going. So how it is working this modified solution? This graph shows undercutting rate in pure and various concentration of NH2OH. So undercutting increasing with increasing NH2H concentration at 15% we observed maximum undercutting rate and that is also 3 times more. This is undercutting rate on 100 surface. This is undercutting rate on 110 surface. This is schematic view before and after wet anisotropic etching. This is mask undercutting takes like convex faces. So this is one of the very important in MEMS application. We want to undercutting some applications like fabrication like cantilever structures, like cantilevers, suspended structures. So we are successfully fabricated this released cantilever structures and different shapes in this modified solution with quickly. See here that images. This is all on 100 surface. This is 110 surface. Modified solution by addition of NH2H solution can be used directly in industrial production of MEMS microstructures with high speed etching. So conclusion, its rate of 100, 110, 111 and silicon dioxide are investigated in few and different concentration of NH2H solution. 15% NH2OH is a optimum concentration where we obtain the highest H rate on 100, 110 and 111. Its selectivity increases significantly with increasing of NH2OH concentration. High selectivity is observed at 15% NH2OH added 28% KO solution. We fabricated fast released structures on 100, 110 in 15% NH2H added 28% KO solution. In addition, surface roughness is not changed considerably in modified solution. Improvement in its rate of crystalline silicon in modified solution follows similarly in different temperatures. Aging effect of modified solution was studied. So, thank you.
Thank you so much for your presentation. Now it's time for the question answer session. I can see there is a question from Shomodip Kundu. Can you please tell about the relation between H rate and industrial production?
So industrial production, we want to quick fabrication. We want to do any industrial slowly because that time is very important in industrial production. So whatever maybe we want to fabricate microstructures with very quickly, it is lot of energy or some saving. So that way it is industrially useful.
Okay, I can't see more questions here. So if anybody can have more questions, they can ask to the speaker in our Slack channel. I would like to request the speaker to upload your slides in our Slack channel. So thank you, Dr. Avareo, for your nice presentation.
Thank you, ma'am.
You can stop sharing now. Let's move on to our next speaker, Ms. Moumita Noshkar from Presidency University, Kolkata. Are you ready?
Yes.
Now it's over to you. Start sharing.
Yes, thank you. Let me share my screen. Is it visible? Hello?
Yes, visible.
Okay. Make it presentation. Okay, so shall I start now?
Yes, you can start.
Okay, thank you. So, good afternoon, everyone. I am Noshkar, a PhD student from Presidency University, Kolkata. And today I am going to talk about effects of magnetic anisotropy on reversal of magnetization in Bloom-Keppel ferromagnet. So first of all, let me mention the plan of my talk. First, I will briefly discuss the metastable state in a magnetic system, its lifetime, associated classical nucleation theory, which explains such dynamical problems nicely. Then I will describe the model and simulation technique. And after that, I will share some various observations regarding reversal or metastable lifetime under the influence of magnetic anisotropy. Then there will be conclusion along with some future scopes, followed by some useful references. So first, how does a metastable state appear in a magnetic system? So that question can be addressed very simply in the light of free energy versus order parameter picture, where this free energy is the Landau free energy, and this is a very well-known picture of free energy versus order parameter for the icing system, where below critical temperature the system has two stable states. Now, and this is in absence of any external field. Now, if we apply some external field to that system and below critical temperature, then we found that immediately this symmetry breaks and local minima appears here along with the presence of a global minima. And this local minima actually indicates here the appearance of the metastable state. Now, if this applied field is sufficient to overcome this energy barrier between this local minima and this global minima, then only this metastable state can decay to this stable state. Am I audible? Hello?
Yes, yes. You are
Okay,
perfectly audible.
yeah, fine. Okay, so now let's say how we have defined the metastable lifetime or reversal time of magnetization. So first, notice this plot magnetization versus time, where initially we have considered a perfectly ordered state. That means almost all the spins are plus one. So magnetization is one here. Now, as we apply some negative field to that system, then it is generally observed that the system first enters into a metastable state, and after a long time, uh, it suddenly decays to this stable state. That means here now the spins try to align along the direction of the applied field. And here quantitatively we have defined the metastable lifetime or the reversal time of magnetization as the time at which this magnetization just becomes uh, starts becoming negative. And uh, and we have used this definition of lifetime or the reversal time throughout our work. Okay, so now how does this metastable state decay to the stable state? And that is nicely explained by the classical nucleation theory, which assumes that the free energy for the formation of droplets of down spins into the sea of up spins is actually formed of two terms. This is the bulk energy term, and the second one is the surface energy term. And due to the competitive nature of these two terms, there must be a presence of critical size of the droplet such that only the droplets with size greater than LC are energetically favored to grow continuously, and only they can take part in the reversal. So the main point is here that the metastable state decays to the stable state through this nucleation process. And later, in 1935, Baker and Doring predicted by some analytical calculations that the rate of such nucleation process is strongly dependent on this energy barrier or this critical energy corresponding to this critical size of the droplet. And so definitely the metastable lifetime also depends on this critical energy. So this is a very brief theoretical background of metastability, but in this work actually we have done simulational studies. And am I audible?
Yes.
Okay, yeah, fine. Okay, so people started such computer simulational studies a long time back, which is around 1970. And there are many important papers on metastability, metastable states, metastable lifetime, etc. And here I am mentioning only three of them, and this is one of such important papers. And here authors studied the metastable states and nucleation in kinetic Ising model. Also, there are some other two papers. In that paper, authors studied the dependence of metastable lifetimes on field, system size, etc. in kinetic Ising model. Here also, authors explored the nucleation and hysteresis in kinetic Ising model. And here also, authors studied the dependence of metastable lifetime on field, system size, etc. in kinetic Ising model. Also, there are some other two papers. In that paper, authors studied the dependence of metastable lifetimes on field, system size, etc. in kinetic Ising model. Here also, authors checked, explored the nucleation and hysteresis in kinetic Ising model. studies which involve some effects of magnetic anisotropy on the metastable lifetimes. So we decided to check such effects. Now, before entering into the model and simulation technique, just let me mention the importance of metastable lifetime. It is generally relevant to the behavior of magnetic storage devices. Suppose suppose a system has smaller metastable lifetime, so definitely its recording speed will be higher. Also, stability of data under any thermal noise or field noise is also important for better longevity of devices. So, in order to prepare some good device, it is necessary to optimize all those issues, and for that, some knowledge about reversal or magnetization in various environments is useful in that sense. And okay, now we are interested in magnetic anisotropy, basically the magnetocrystalline anisotropy, because it plays a crucial role on magnetic behaviors, and it generally arises from different crystal structures. And due to this anisotropy, spins prefer to align along a particular different direction, often disregarding the direction of external field, and so the system possesses different magnetic properties or behaviors along different directions. So it's important to study such effect. So how does this anisotropy affect the metastable lifetime? Am I audible?
Yes, you are.
Hello.
Yes, you are.
Okay. Okay. Yeah. Fine. So we have studied such effect by simulating Bloom-Kapell model, which is the simplest model to which can give us some insights about such effect of magnetic anisotropy by incorporating this extra anisotropic term here uh, in comparison to the Ising model. And we have simulated this model by Monte Carlo simulation technique with Metropolis algorithm, Metropolis transition probability. And we have considered a square lattice with periodic boundary conditions on both sides. Lattice size is 100 here. And initially, we started the simulation by considering the system in perfectly ordered state. That means all the spins are plus 1. Now, after applying a negative field to that lattice, we have updated the lattice by random updating scheme using this Metropolis transition probability. And the updating process or the algorithm is here in details. Now, first of all, we have checked the magnetization with time for different strains of anisotropy, and we found that the reversal time or the lifetime decreases with increasing strength of anisotropy. And also the saturation magnetization, is there any question? Okay, I'll check later. Uh, so also the saturation magnetization varies with this strength of anisotropy. So here we have studied the variation of this absolute value of MF with anisotropy for different values of different strains of field, and we found a scaling behavior between them. And this scaled data actually indicates different kinds of magnetic ordering depending on the strength of anisotropy. Because notice here that when d is 0 or in the large limit of negative anisotropy, magnetization is 1, which indicates a perfect uh, ordering of the spins, and which is basically influenced by the external applied field. But as we increase the d and in the large limit of positive d, the magnetization becomes 0. So that immediately it seems that there is no magnetic ordering, but this is actually not true, because here the system possesses a different kind of magnetic ordering, which is in perpendicular direction to the z-axis, and which is basically influenced by anisotropy, not by the external field. Now, since we are simulating the system statistically, so here we have presented uh, 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 probability distribution of reversal times obtained from 10,000 different samples. And we found that the peak position or the most probable reversal time also its standard deviation increases with decreasing strength of anisotropy. And since a statistical distribution is present here, so it's better to proceed with mean or the average value of reversal time and to check its variation with both the positive and negative anisotropy. So actually, if we merge these two plots, then it is a same line, but here we have presented it separately because the sign of D has different physical significance. Because in the large limit of positive anisotropy, z-axis becomes the hard axis, and so the spins try to align along a different direction perpendicular to the z-axis, and in that case, it is much more easier to flip such spin from 1 to 0 state, and that is why the energy barrier decreases and also the metastable lifetime decreases with D. But in contrast, in the large limit of negative anisotropy, z-axis becomes the easy axis, and then the Bloom-Keppel system behaves like an Ising system. And in that case, the spins try to acquire either in 1 or -1 state, and so its energy barrier of the metastable lifetime also increases because it need large energy to flip the spin from +1 to -1 state, and that is why here the lifetime also increases. So by combining these two variations, we can express mathematically in this way. Now here a temporal variation of density of different spins is provided just for a better clarification. Am I audible?
Yes, you are. Yes, you are.
Okay, yeah, fine. So here is the plot for density of all the spins with time. And for a large value of negative anisotropy, we found here that the spins are either in +1 or -1 state, and the density of spin 0 is almost 0 here. But as we increase the positive anisotropy, we found here the active role of the density, active role of the spin 0, and which indicates that the z-axis then becomes hard axis. Now, can we somehow connect the macroscopic mean reversal time with the microscopic reversal time or switching time? For that, since we are studying the influence of anisotropy, so here we have chosen only those zero spins which are surrounded by all the 4+1 spins. And we found that this density of such zero spins decays exponentially with time, and we define the microscopic switching time from this expression, the inverse of B, and which is denoted by tau A. Now, for each D, we have calculated tau A, and also for each values of D, we have mean reversal time also. So now, if I plot this tau A with our mean macroscopic reversal time, we found that there is a linear relationship between them. Now, this is very interesting. So we can connect the macroscopic reversal time with the microscopic time. Now, since we are dealing with finite lattice size, so we have studied here the reversal time with D for different system sizes. And from both the quantitative and qualitative point of view, the data seems to be remains same, disregarding the size of the lattice. But actually, there is a very small quantitative deviation. However, this deviation is much more prominent for in the errors or standard deviation of the reversal times. And lastly, Abraham's law depicts that close to the critical temperature, the metastable volume fraction decays exponentially with this power. And since we are studying a 2D system, so we have plotted here the logarithm of metastable volume fraction with time cube, where this metastable volume fraction is nothing but the density of spin +1. And so from this linear fit of the data, this linear fit of data confirms that the anisotropic system also obeys the Abraham's law, and also at a certain time fraction, one can confirm that for a large anisotropy, this larger value of this quantity confirms that this density of spin +1 is smaller, and that confirms also the faster reversal for large positive anisotropy.
Sorry for the interruption.
Yes,
Sorry for the interruption.
yes,
Your
yes.
15 minutes are over, so please try to
Okay,
conclude.
yeah, it's almost over. So, at conclusion, we can say that the magnetic anisotropy can influence the metastable lifetime, and macroscopic reversal time is well connected to the microscopic scale of time. And Abraham's law holds good in anisotropic system also. Now, as a side remark, I'd like to say that it would be interesting if someone tries to modify or upgrade the Becker-Doring theory analytically so that it can accommodate such influence of anisotropy. And also, real material hardly follows this dynamics that I have used here in Monte Carlo simulation. So definitely there will be some quantitative deviations of results with in compared to the real experimental results. And okay, and so as a future scope, one can definitely check such effects in continuous spin models. And since we are studying the magnetic anisotropy, so it is uh, uh, we can advise that someone also can check some distribution of anisotropy or anisotropic disorder, or some kind of surface anisotropy, etc. Okay, so this is our published paper, and I want to acknowledge that scholarship, and I am grateful to my supervisor, Professor Muktish Acharya, for a lot of discussions, and thank you for your kind attention.
Thank you so much for the wonderful talk. Now
Thank you.
it's time for the question answer session. I can see there is a question from Shovik. Is there any specific reason for choosing the Metropolis algorithm?
Metropolis algorithm. Uh, can not so specific reason. You can also use some other Glauber dynamics also. Um, and that much. Okay.
Yeah, yeah. The next question is
Okay.
from Shomodip Kundu. How
Why z-axis was hard axis? Can you make it more clear? Yeah. Okay, let me go to the. Uh, yes, yes. Actually, okay, so here I can say also. Uh, yeah, so okay, for when we apply some positive anisotropy, am I audible?
yes, you are audible.
Yes, Momita, you
Yeah.
are.
Yes, yes. So in when we apply some positive anisotropy, so z-axis uh, uh, in general we are dealing with the z component of the spins, and when we apply some anisotropy, so it anisotropy basically arises from the different crystal structures. So, and due to this structure, many ferromagnets have some different intrinsic, some different direction in which spin can prefer to align. So in that case, then z-axis
Uh,
becomes the hard
no,
axis for them, and the spin.
Momita,
Yes, yes.
try to give the answer from the Hamiltonian and the energy minimum principle. Just go to the Hamiltonian and show
Okay.
the term that is related to the anisotropy, and check whether this, if the
Yes.
z axis is hard axis, the energy will be minimum in that case.
Uh, yes, actually, the so when you put here the d siz equals to +1 or -1, then your energy, and when you put siz 0, so there is a energy splitting. Okay, and in that case, the energy. Am I audible?
Yes, you are.
And yes, and the energy corresponding to this spin 0 is a minimum here.
Okay.
Okay, so the spins then try to align in a different direction, which is perpendicular to the z direction. That means the spins acquire then the try to acquire the zero state,
Okay.
rather the plus 1 or -1 state, like the Ising system.
Okay. Okay. Thank you,
Okay,
Bhumika.
actually the energy is minimized if the spins try to align in a different direction, and that is the effect of anisotropy.
Okay. Okay. Yeah. Yeah. I understand. Thank you. Thank you.
Okay, and that basically arises from the crystal structures. It some structure has different easy axis or hard axis.
Okay. Okay.
Okay, okay.
So the next
Uh,
question is from Shomodip Kundu. How the metastability is tackled using this approach?
Uh, Using this approach means Metropolis algorithm.
Yes,
How the
I think
metastability
actually
is
he is
tackled?
meaning that the metastable diverging points, right? The plot is generated. I think he is meaning that portion.
Metastable diverging point.
That is
Where?
when the metropolis algorithm is applied on the metastable behavior of that ferromagnet. I think he is referring to that point.
Mm, Let me check the question. How the metastability is tackled using this approach? Mm,
Shomodip, can you specify your question?
yes, Shomadip.
It will be better if you can ask directly.
Yeah, yeah. Decay of metastable state to the stable state. Yeah. Hello?
Yes. Just carry on.
Yes. Not symmetric or hello?
Yes, you can speak out. Everybody is listening. We can hear you.
Shomadip?
um,
Shomodip, are you listening? Or you have an issue with
Shomudip?
microphone?
Yes, Shomodev is there, I think. Shomodev is there. I think he's facing some network
Uh,
issue. Okay.
maybe, but I think he can hear actually.
He can hear us. He can hear us. Oh, yes. He's saying that I am writing. He's saying that he's writing.
Okay, fine.
Okay. Or how the Monte Carlo simulation or something. I don't know. I want to know about the non-similarity in the both sides of the graph. Uh, yes, that appears due to the Zeeman energy term. Here, when we apply some external magnetic field, so after adding this term, it immediately breaks the symmetry, right? And one of this stable state, then its energy rises and it becomes metastable.
Yes, this is basically the symmetry breaking term that is working here.
This happens due to this term here,
Yeah,
Zeeman energy
exactly.
term.
Right.
That is
And
the symmetry breaking term actually, as you mentioned.
yes,
Yes.
you are subtracting this image, then definitely there will be some deviation from this to this point, and at another point it just opposite. Plus m and minus m.
Right.
Okay. So there is another question from Dr. Ashif Akram. Dr. Akram, you can ask the
Yeah,
speaker
yeah.
your question.
Momita, can you go to the conclusion slide?
Okay, yeah. Hmm. Yes.
Yeah. So you are saying that macroscopic metastable lifetime is well connected to the microscopic time. So
Yes.
I may
Yes.
have missed the in between slides. Uh, so this point is actually not clear how you are equating the
Yes.
two.
Here in this slide, I talked about it. That macroscopic reversal time is that I initially told about you here. That this is suppose this point. So this is for a single sample, the reversal time, and this one is for d minus 0.5. So this is for a single sample. Now, when we take 10,000 different samples, then we have such statistical distribution of these reversal times, and that's why we have taken the mean of such reversal times. And this tau average is the mean reversal time. Now we have tried here to connect this mean macroscopic reversal time with some internal microscopic scale up time, and that is defined here by choosing only those zero spins which are surrounded by plus one. Okay, the zero spin is at center, and there are four plus one nearest neighbors. Okay, and
No,
we have studied the decay of the density of those zero spins, because these are responsible for the the decay of the metastable state, and that we observed that it decays exponentially with time, and we define this tau a from here. This 1 by b, t is 1 by b, so it is actually the when the rho is 1 by exponential of the initial density, right?
mhm.
Now we have plotted this tau a with tau, and we found a linear relationship between them.
Okay. So is there any theoretical reason why they are connected? Um,
Uh,
Obviously, we can see that they are linearly connected, but is
yes,
did you?
actually, the macroscopic reversal is occurring uh, uh, yeah, when there is some microscopic switching occurs. So definitely there is a reversal time of doesn't happen suddenly. Something decays with time, and that helps finally to reverse this reversal. I'm showing here Monte Carlo simulation. So
What I'm saying
yes.
is tau by
Hmm.
tau a. If you take the slope, actual slope of the experiments, will that be order one like here, or it will be some order 10 or higher order?
No, no, definitely tau is greater than tau a.
No,
So if
that I understand. What I'm saying is
yeah,
tau by tau a is it order one um, thing,
uh,
or it's the
okay,
order?
no, I don't know the order. No,
Okay, fine, fine.
yeah, that can be checked experimentally, I think, or some other simulation technique, uh, molecular dynamics, or I don't know. I don't have idea on that. But from Monte Carlo simulation, I can't give you this idea of order, I think.
No, Movita, that order can be checked from this diagram. If you see this tau A versus tau, uh,
Yes.
So you can, at any point on the straight line, if you take the ratio tau by tau a,
Yes,
so that will give you the order roughly.
yes, that I can check. So this is basically
That
A,
is
I think,
the
value of
that is
A.
precisely Dr. Ashif Akram is asking. I think so.
Yeah,
Yeah,
so this
yeah,
is the value of A, I think, here. Ax, the slope of the plot, right?
yeah, yeah. It's order one. I have understood. Fine.
Yeah. Okay.
Nice work.
Okay. Thank you.
So I don't see any more questions. Thank you, the speaker, for very wonderful talk and also very encouraging question answer session. You can stop sharing now.
Okay. Thank you. Thank you so
You
much.
can continue the discussion in the
Stop
Slack channel,
presenting.
and I
Okay.
request you all to upload your slides in our Slack channel. And there are also videos uploaded already in the Slack channel. Please have a look at them. So now we are at the end of our oral presentation session for day one. Now it's over to you, Shobik.
Okay, am I audible? Hello?
Yes, you are audible.
Okay, so we are at the end of our day one of this conference, and I would like to sincerely thank each and every participant, every mentors, every plenary speakers, and all the conveners for their effort. There were very nice talks. All of us, I hope, have participated very well in this. And just for a few moments, let me share the screen for our next day
So we
schedule.
also tell everyone that to fill up the Google form that is floated in the chat box for
Yes,
getting
actually,
certificate.
that is true. So I see 23 people are there. So if possible, please fill the Google form which is given in the chat box, that is for the certificate purpose. So please fill the form as soon as possible, and let me share the screen. I hope my screen is visible. So this is the schedule for the next day, that is day 2 of our ICCMSP. And we have two plenary talks tomorrow. One is from 10:45 a.m. and another is from 2:30 p.m. and four oral presentations just like today. So I cordially invite all of you who have participated today and heartily thank.
So looking forward to an exciting session tomorrow. Thanks everybody.
Okay, thank you.
Hello?
Okay, thank you.
Hello?
Hello.
Can you share this link via email? Or I have to fill it here?
Okay, well, I think we shall share it via email.
We will share it by email afterwards. No problem.
Okay,
Okay. Okay. Yeah. 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 Thank you.
thank you. Thank you all. So I'm signing off.